Alright, so this is going to be the beginner video for what I'm going to talk about on black holes and space-time and general relativity. It's really freaking cool. I really recommend you get through these videos and get to the ending. And I'm going to have to show some graphs. I don't have them with me right now, so I guess that will have to wait for the next video. Actually, I'm not sure if I can do it without. I probably can get through some of the basics first for, people who've never really gotten that. But, watch this video anyway, even if you think you know more. But let's get into it. So, space and time. What do we mean by space-time? Well, space and time are actually very fundamentally linked. Like, the most basic example I could give is, well, if you can go to the same location, two objects can go to the same location, but they won't interact with each other unless they go to that same location and the same location in time. So time and space are both a connected coordinate, all right? Nothing happens unless it's at the same space at the same time. And each space and time is, an individual thing. Okay. So, then also, it's, four-dimensional. The universe, everything is four-dimensional. You are not just what you are in a single slice of time, you're throughout your lifetime. You're four-dimensional. And a 4D object doesn't look like the Tesseract. If you really want to make it like an object, basically a 4D object would be like if you connected lines to like all of the spaces and times that I have existed, and that that's why you get all those little sides on the inside of each other and moving around, is because all those sides are inside of each other. It's a three-dimensional object smeared in all of the different ways that it existed between 2 points of time. That's a 4D object. And that's why you get all those little moving bits and, yeah. And, so, alright, get past those. So what is gravity really? Most people think of it as a force, which is not really true. It's not really a force. It's, the curvature and the movement of space and time. And so why do we go down? Well, actually, we're going up because the space we occupy is moving down. It's falling. And, the space that all of the atoms beneath you is falling. So if the space you're in is moving, you don't have to move, and you still, move. But you're not actually moving in space. The space you're in is moving. And then they get close to each other, and they, through the electromagnetic force, they repel. That's how touch works. It's electric forces repelling each other, because atoms are pretty much electricity and energy and particles. And then they push up. So literally, we're moving up right now. If you're falling, the earth is coming to you. You are not moving. Okay. Now for a black hole. What is a black hole? Well, a shit ton of matter after a star dies, it collapses, you know, and collapses to the point where there's so much gravity that the rebound won't, you know, like can't get out, and it just collapses anyway, and it just like you know, there's so much space or so much stuff in such a small space that, you know, space around it, the black part of the black hole, moves so fast that it moves faster than light. And light is the cosmic speed limit. Anything that has mass would require infinite energy to move faster, or to move at the speed of light. It's literally impossible. And anything that doesn't have mass must move at the speed of light, nothing less, nothing more. And the speed of light isn't actually about light at all. What it is it's about the cause and effect. Okay? It's literally, it's, you know, the speed at which something that happens here can affect this point in space and time. How much, you know, how fast will it, or how long will it take to affect this space? And that speed is the speed of light. And so, in, you know, like relative terms, in a way, literally, like, you can think of those causes, you know, cause and effect. That is time. That is 100% what time is. It's effects and causes and effects. That's what the dimension of time is. It moves forward, right? You can think of the past moment expanding infinite, like, you know, expanding in all directions at the speed of light. Every moment. Like this moment, you know, that's your light cone, basically. That's how fast the cause can affect something. And you know, the future is always in the tiny, or the now is always being like replaced, sort of. Now, and that's another, you know, another interesting thought, but I'll get to that. So basically, if, you know, that is true, that the past is, you know, in all directions expanding at the speed of light, light only exists at the point in time that it was born. It doesn't experience time. It doesn't experience cause and effect. It is in that moment traveling with it forever until it hits something else and it becomes a new moment. Or it gets, you know, transferred into another form of energy. And so, you know, at the speed of light, that's, you know, the fastest something that can possibly affect another thing. And, you know, in a sense, the only things that experience time are massive things. Things that have some mass. You know, any mass at all. That is what mass is. It's the interaction of time. So, having that out, and trust me, this will make more sense in the following videos. Okay? But we have to cover this first. Okay. Now, at a black hole, the reason it is black is because space is moving so fast that light can't get out. Cause and effect can't reach the outside universe. Nothing that happens in this in this region of space can ever affect anything in this universe. And, if you were on the outside of a black hole, right? Just like outside, you would see a bunch of weird shit. And, we're gonna set the scene. Okay, there's a black hole, you're on the outside, and then your friend is, you're like right, you're close to the event horizon, which is the outer layer of the black part. And your friend is on another planet far away, but he's watching you. And, okay. What do we see? Because general relativity is all about how things, spaces and times interact with each other and what's possible at speeds and, what you are relative to someone else. Because, when you're driving near and two cars are driving next to each other at the same speed, you don't move to each other. Relative to each other, you're not moving at all. And the point of view of any, particle in the universe, the rest of the universe is moving compared to them, and they're always stationary to their reference point. That's not entirely true, obviously, but to their reference point, that is the case. And so, at your reference point, what you see the entire universe speed up. You see trillions of years, or not trillions, but thousands of years go off in seconds. And eventually millions, then billions, then trillions as you fall deeper and deeper. But you see the whole future history of the universe pretty much in flash. It would be pretty damn beautiful. Your friend sees you slow down and almost move in slow motion. Why does this happen? Well, think about it. Space is moving so fast where you are. You can only possibly move so much in each frame of space and time. There's only so much you can do. But your friend, whose spaces and times are moving much slower, they can do a lot more in each space and time. So every frame of space and time, depending on its speed, like the slower you are, the more your speed actually does things, and then, you can do more in that frame of space and time than they can, or you can in this scenario. Okay, that's called time dilation. And as you go into the black hole, the horizon comes up to meet you, but it's not like, being enveloped into something and then going, like, it's not in front of you. If you're looking out to the exterior world universe, it almost like it forms around, and then it becomes like this circular view as light can reach you from fewer directions. And what it's doing is literally it's curving space-time. So all of these other locations over here are being curved inward to be this direction. So the farther you go in, the smaller and smaller that little hole of the universe gets. Now, because the bending is so radical, literally any direction you go in leads to the black hole. So if you happen to be in this unfortunate scenario, to survive the longest, do nothing. Because if you start accelerating to the outside of the black hole, you will actually be going further in. You will be going to the center faster. And then, you get what is a legit term, spaghettification. You get, the space and time gets funneled so thin that all the spaces of your atoms are getting farther and farther apart. So you're getting thinner, or like you're getting stretched and you're getting thinner. And then just like everything just into a long, thin, little string. You're becoming a singularity. Okay? And yeah. And so I can't wait to get the graphs. Okay. And what else? Right, length, uh, what is it called? Length something. No. Length contraction? Yes, length contraction. That's a very interesting thing, but I'll leave that for the next video. What else should I talk about? Well, you also get the cool effects of light, because, around, on the outside of the black hole, um, you know, it's so bent that light is orbiting. So if you're outside the black hole, in pretty much every direction, you just see yourself. Because, or if you turn to the right or to the left, you just see the back of your own head as the light travels around the black hole to your eyes. And it's just a weird, literal funhouse mirror. Um, and, yeah. And, also, one thing to note, everything I just told you is more or less, it's correct, but everything I just told you is the description of a theoretical black hole. Black holes exist, but everything I said will be completely transformed when I add one thing, which is the fact that black holes spin. And that changes absolutely everything. Everything, oh shit. Everything you know about black holes is about to get so much cooler. Simply because they spin, which, oh my god, it changes everything. And then later, I'm gonna go, about the Big Bang some more, but for another reason. And, yeah, this will be a cool series. And if you have any questions, or, want to say something that I haven't gone over, please ask me your questions, because, I don't know how well y'all are understanding this. These are some heavy topics. Took me a while to figure out and understand. And it'll be much easier if you were right here, so I could, know what you're thinking and how you're thinking. And this will be a lot easier in the next video when I have graphs and, you know, stuff I write down to visualize it. And space-time is cool. Science is cool. And Einstein is a badass. See you in the next video.